Konstantin, so first time I heard about Prime Intellect was in November 2024, when you just had finished a training of a 10 billion parameter model, not for the first time in the world, but the first time decentralized over 3 continents. And that was a huge thing, and yeah, I think TNG even offered some GPUs also for helping there, but yeah, you already had enough for that. And then lately, you and Prime Intellect, you resurfaced in our AI discussions when it came to fine-tuning. And so far, we were always like thinking for our customers, this is not really the thing to go because it's really demanding and yeah, technically, it's really not easy. And maybe it's even outdated quickly by newer models. But this might change now with reinforcement learning pipelines, and this we'll see today. And that's why I'm thrilled to announce our next speaker, research engineer at Prime Intellect. He works on reinforcement learning for LLMs and the whole stack. So from training the infrastructure to really the basic research, fundamental research. Some of you might know him from the ex-innovators, AI innovators bubble Accelerate. So please give a warm welcome to Konstantin Dunas from Prime Intellect.
Hello, everyone, and thanks, Florian, for the kind introduction. And though I would like to take credit for what Prime did about the 10 billion parameter model, I really can't because I just recently joined. So I'm not really here to talk about decentralized training, though, of course, that's also quite interesting. But as you can see, I'm here to talk about reinforcement learning, and specifically for LLMs in this new age that we find ourselves in, which I call the age of agents. And I think you've all heard about LLM agents and agent here, agentic this. And so the question is the hype that surrounds this topic warranted, or is it just a fad that will come and go and be replaced by another thing in a few years? And well, to just take it straight away, I think it's not hype at all, even though everyone is talking about it. As a matter of fact, since coding agents came out, I have not written a single line of code myself in 2026. I mean, my agents wrote a lot of lines of code in my name, tens of thousands even already by this year. But of course, this is not the software engineering that we've been doing for decades now. As a matter of fact, I would argue that many companies now do software engineering quite differently. And even a lot of legacy corporate companies in Germany that I've talked to actually told me that all of their employees get Cloud Code subscriptions and they use it quite a bit. And I think it still has not really settled in yet that with enough agency and with enough creativity that we can basically, as an individual now, do something that would have been impossible even for a small team to do just a few months ago. So this is just to already take away that, yes, I think agents, the hype surrounding them is warranted. And as you can see here, I have this meme where I'm asking Cloud Code to create this presentation and make no mistakes, of course, because if you don't say that, then it will make mistakes. But in truth, of course, the models, especially these coding agents, they're not that good at making presentations. So unfortunately, I still had to do that one myself. Maybe the next one that I will be doing will be also AI generated. But the question then becomes, how did we get here so quickly? Because every one of you might still remember maybe even just a year ago when hallucinations were so rampant that it was really not possible without tight supervision to use these coding agents to do meaningful work. And then, of course, the question might also come to you, that is, where are we going with this? Where are we headed? What are the next frontiers that we are going to go towards? And these are basically the things that I want to talk about. So first of all, I want to explain what is reinforcement learning, and specifically what is reinforcement learning for LLMs, because it's quite different in practice than the classical reinforcement learning that some of you may be used to. Then how do we scale it up with LLMs in particular? And the scaling of it will be a big component, because it may sound like you can just throw more GPUs at it, but actually the infrastructure behind all of this is quite complex. And finally, I will just speculate a bit into some research directions that I find quite interesting and that I think could tell us what may come next. So just as a reminder, maybe you were already in AI at the time, or maybe you had read the news in 2016, roughly 10 years ago. AlphaGo beat Lee Sedol, grandmaster at Go, Go being a very complicated board game, much more complicated than chess, really. And AlphaGo was a model trained by Google DeepMind, and it was just trained to play Go. It was never taught these rules. It just learned them from exploring and playing enough games against itself. And it culminated in the defeat of a grandmaster, which was quite amazing at the time. And just 2 years later, OpenAI even topped that with OpenAI 5, where they beat a professional esports team at Dota 2. Dota 2 being an even more complex game where you have multiple agents that the model has to control at the same time, and it's a real-time strategy game, so you can't just really think about your turn, you must act quickly. And these were quite big achievements, and it has been dubbed then that reinforcement learning is capable of going to superhuman levels at basically anything that you really want to, or so it seemed maybe. However, what really is reinforcement learning then? In essence, it's just a paradigm of machine learning where you have an agent, and that agent gets a state that is the state of the environment, because the agent lives in an environment, and it can interact with this environment by emitting actions, essentially. And then this environment changes, and this change in the environment emits a new state, and it emits a reward that the agent can then later use in the algorithms for learning and updating its policy. The policy being, the policy being this thing here, this pi of a given S, which is just a probability distribution over the actions given the state. And this is what we're really learning here, a parameterized version of that, essentially. This is what the neural net represents. So reinforcement learning is just a paradigm, and if it's such a powerful paradigm that has already gotten us to superhuman abilities, a natural question would be, why have many people not heard of it? Or why has it been relegated to other domains instead of, well, the ones that language models were doing just a few years ago, like software engineering, even though they did not do it well, of course. And now there's, I would argue, 3 reasons for that. 2 of them are kind of solvable, but the last one is really the problem. So the first 2 reasons are that the state space and the action space of many tasks that we want to solve, like software engineering or research or being a lawyer or being an accountant, are just gigantic. And it's very difficult to train a model from scratch to be able to do that. You would need a lot of training data, you would need a lot of time. And in particular, all of these models, if you train them from scratch, they do not really generalize. They actually don't generalize at all. Sometimes it's even so that if you take a model that was trained on, say, Go, and then want to let it play chess, what happens is that the model cannot even play chess, because the way that the action space works is that it is such a different representation that the other model cannot even emit an action. And so this, what I dub reinforcement learning from scratch, where you start out from nothing and train one model, does not generalize. And this had been quite a big problem, because of course what people like Demis Hassabis from DeepMind and Shane Legg and many others were saying was that they want to work on artificial general intelligence, AGI. And of course you're not going to get there if you have to retrain for every, there's nothing general about this, right? If you have to have a model for each task. In the meantime, while the hype for RL was dying down, another hype was emerging slowly but surely, and that was that of large language models. And that was around 2020 to 2022. And here are 2 seminal papers, one from 2020, one from 2022. And it was really in this time when this paradigm of language modeling gained quite some traction, both with OpenAI and DeepMind, and those were the dominant players at the time, and Facebook AI research was a third one that was quite relevant. And essentially what people found is that if you take language models and you do train them in a self-supervised manner, where you just let them predict the next token, a token just being the next text you can imagine, then these models, if you scale up the training data enough, and if you scale up the parameter size enough, that these models show emergent behavior. Apparently, if you show them some examples, they can follow this example and do the same thing, right, that then in these examples. They can adapt, and this emergent behavior was quite fascinating at the time. And essentially, what it showed is that there's something like generality that was missing from reinforcement learning from scratch that we can get through these base models when we train them on large enough data. And this, of course, culminated in the release of ChatGPT, which really ignited the hype with, well, everyone basically, became a success overnight, and that was by the end of 2022. And essentially, the recipe for ChatGPT was really threefold. So on the one hand, you had this pre-trained base model, which was trained on all the text that you could find on the internet, on scans of books, on archived documents, on whatever you can get your hands on. And then, of course, this model, it was, because of the way that it was trained, it was just a next token predictor. So it could only autocomplete in a sense and give you the next plausible token based on everything that it had seen. So what people found is that if you do some instruction tuning, which is the process of showing the model a lot of conversations that are between a user and a helpful assistant, that the model can actually learn not only to just autocomplete with what is most plausible, but to follow instructions and do as the human basically wants it to do. And then finally, because the models could be quite unhinged and they did not really have any guardrails, people found that you can use reinforcement learning from human feedback, RLHF, to kind of rein this in and align the model to human preferences, to be harmless, to be helpful, to not say slurs, and so on and so forth. But this reinforcement learning, just note, even though it is named reinforcement learning, is really of a different kind and of a different, it's qualitatively different than what people used to do and what they hoped they would get, and what we do now. It's just this intermediate thing that is just formally related to the other two. But you should really not think about this when I say that we're doing reinforcement learning. But then the question arises, right? You've all used ChatGPT. It's just a text bot. It's just a chatbot. It just emits text. You give it some input text and gives you some output text. So it's not really an agent in itself, right? If we think about what an agent is, it has to be in an environment, it has to be embodied, it has to be able to interact and act in general. And the missing piece at that time, which was also developed in 2022 and especially in 2023 and so on, were tools. And you can imagine that, of course, chatbots only being able to output text, you can make them output text that is structured in a way that you can parse out an action from the text, right? I mean, you can just represent the actions via text. And then these tool calls, you get them, you parse them out, you execute them yourself, and you feed back the result to the model. And this basically closes also the loop that the model has to have with an environment. And you can see a pretty interesting example here where you have the user which asks this question, so evaluate this integral, and then you can think about the LLM thinking about it and saying, okay, this matches a standard zeta function integral. I'll verify it with a symbolic math tool. And then it uses this symbolic math tool, it calls it with this tool call, and the tool name then is, let's say, integrate. And you have to feed it these expressions, and it has to be formatted in exactly this way. We can then later parse this out, call it in the code that we have on our client side, and then we can return the result to the LLM, and the LLM can tell the user, hey, this is actually the result. And of course, this is quite powerful if taken to its extreme, and as a matter of fact, this is how you can actually meaningfully do reinforcement learning, the one that I was talking earlier with LLMs. Because then the state just becomes the conversation that the LLM had so far with the human. So it's the system prompt, the user prompt, the thinking of the model, and so on. And then at some point, the model says, okay, now I can't really get further with my thinking. What I need to do is I need to call an action. I need to call an API. I can't really have this information without, maybe I'm unsure because I'm not sure if I will do the calculation correctly, or maybe the information is not even available to me, so I have to query an API or look something up. And so it does that, it sends it back to us, we execute this, we are the environment in a sense. We attach the tool response to the past conversation, and this is then the new state that we can send back to the model and let it keep thinking and keep doing a tool call, and so on and so forth. And that's how you essentially get this earlier formalization of reinforcement learning with LLMs. And of course, this is very simplified. It's much more complicated than that, and maybe some people who are also deep in this would disagree that only this constitutes reinforcement learning with LLMs, because there's, of course, also the entire reasoning paradigm where there are no tool calls and the model just thinks for a very long time and so on. But I would say that for the coding agents, this is the framing of RL that makes most sense. And then, of course, I said at the beginning, so now we know what reinforcement learning is and how to do it with LLMs, but it's of course not enough to just know how to do it. We need to do it at scale. And actually, I really want to take some time and talk about why the scaling of reinforcement learning with LLMs is very different and actually, in my opinion, much harder, though of course this is contentious, than pre-training. Because the pre-training, that is taking these large corpora of text and just feeding them into the model and so on, you have these static data sets that, yes, you need to spend a lot of time collecting them and filtering them and maybe even generating more data to fill the gaps and so on. So really, there's a lot of data work that goes in there. But then you use all of your GPUs that you have essentially for training. So you just partition the data set onto each GPU, essentially, and you can just train. And it's quite simple as soon as you have the data. And you can reuse the data for later runs. So in a sense, it's very nice. Reinforcement learning, on the other hand, is much more difficult to scale. Because, first of all, you have to generate these rollouts, that is, these state action pairs that you do in a loop until the model says, OK, I'm done. You have to generate these rollouts online. You can't just let another model generate them. And you also can't let a previous model generation generate them, because these rollouts have to be close enough to the policy that we currently have to be able to properly integrate them into our algorithms. But that also means that you have to host the LLM itself on another set of GPUs so that you can actually do inference with it. And furthermore, then, not only do you have to do all that, you have to build tasks that have exactly right difficulty. Because if they are too easy or too hard, the model will not learn. Finally, you need to define how the LLM interacts with these tasks. That is to say, you need to build a harness. A harness is something like Cloud Code. I will talk about all of these things in more detail a bit later. So I will just go through them very quickly here. You will also need something like sandboxes. So because as soon as you have these stateful things, as soon as you have these repositories or whatever else, you basically need to upload the task into a sandbox. And then you need to install the harness, which is just a CLI tool, also into that sandbox. And then you need to execute in that sandbox. And the cost of the sandboxes actually is a very big factor. And to do this efficiently is actually one of the biggest engineering challenges that we had to face and are still facing. And then finally, of course, because of the way that we do, because of the way that the setup is, you also need an algorithm that can handle stale rollouts. And this is actually one of the most interesting areas of research, in my opinion. But it's quite technical to fully understand, so I will not talk too much about that here. Right, so let's begin by talking about tasks. What even is a task now? I mean, for pre-training, it kind of makes sense. You just have a data set, so you just have like text. But a task, essentially, first of all, you can think about task sets being the new data sets, where a task set is just a collection of tasks. And these tasks, usually to be part of the same task set, share some underlying mechanism or have some similarity of some sorts. And then you have multiple of these task sets, and this is what you train on. Each singular task from each task set consists of multiple things. Now, it does not have to have all of these things. Sometimes this is up to interpretation, but usually it should be well specified so it can be reproducible. One of these things is an instruction. The task has to, of course, consist of what the text is that the LLM will be initialized to basically say, hey, this is what you're going to do. You have to solve, for example, this GitHub issue. So an instruction in natural language. Then you have many files and assets, maybe the repository of the code, maybe a bunch of documents that you need to search through. All of these things have to be uploaded into the sandbox, and oftentimes they come baked into a Docker image already. Finally, you need to say, okay, what are the resources that the sandbox is going to need? Not every task has the same constraints. Some tasks may need GPUs, some tasks may only need CPUs, some tasks may need a lot of memory, sometimes some tasks may need a lot of disk space. So you kind of have to define the resources such that later in the orchestration of this, we know what kind of sandbox to create in the first place. Further, you need to have all of these setup requirements, so which programs need to be, so how does the setup work? Where does the sandbox image live? What do we have to install from where, and so on? And to do this in a unified way can get quite complicated, and we've taken a long time to nail an abstraction that we believe is quite nice, which is this task set abstraction, which I will talk more about a bit later as well. And finally, of course, just having a task is not enough. You need to have a way where you can assign reward to the task, so we know whether the LLM actually did a good job in solving this task. So this is something like a verifier, or for coding, this can be unit tests that you then upload to the task sandbox, and so on and so forth. Okay, let's talk about the right level of difficulty. So I have two plots here. They're of course AI generated, because plots are never this beautiful and clean in practice. But let's think about the first thing here, which says reinforcement learning has a cold start problem. And the reason for that, or what does this mean? It means if you take a model that is just a base model, so it's not accustomed to answering in a structured way yet, or it's just not as good yet. The problem is that the task at hand might be too difficult. And if the task at hand is too difficult, what that means essentially is that the model will always get a reward of 0. And now reinforcement learning needs this variance, it needs this contrast of rollouts that were good and rollouts that were bad, as to reinforce or de-enforce certain behavior. And so if a task is too difficult or too easy, then the model cannot learn. If the task is perfectly difficult, that is, the difficulty is perfectly adjusted to the capabilities of the model, then the curve may look like the one on the right. This can happen sometimes, it's quite rare, and whenever it does happen, you feel the sense of joy that you did something right with the curriculum. And it's quite satisfying, but it's very hard to nail for large-scale data task sets. Okay, so these were tasks. Let's talk about the harness. A harness, I would argue, and this is my definition, yours may vary, but for the sake of this presentation, when I say harness, I mean that this is the thing that takes the LLM and makes it an agent. So whatever it is that allows the LLM to interact with an environment is the harness. And this is something like the tools, which we discussed earlier, right? So you have to have tools that can be executed. This is the harness's job. You can also add further scaffolding. So you can have something like context management, like as you can see here, this compact, maybe if you've used Claude Code, you've seen this. You can just compact the past such that you can then not run out of context, because of course LLMs have a limited context window. Maybe there's something like persistent memory, like I think certain scaffolds like OpenClaw and Hermes agent have that, where they persist memories in between user sessions, though I'm not too sure about how they do that. Finally, it can also be something like the control flow is different, so maybe you want to call sub-agents or whatever, but you want to do something that is not just a linear rollout, and the harness basically handles all of this. Okay, so we have task sets and harnesses. Now we can talk about, we can go through the training of an agent with RL. So first you do the setup, you sample one task from the task set, you create a sandbox from the task image, and you basically do all the setup, you upload all the task files, you install the harness, because the harness is of course just a program, and then you call that harness, like Claude Code or Codex or whatever, with the instruction from the task. And this basically just initializes the harness and basically simulates the user in a sense to basically kick off this rollout loop. Right, and the next step then is just the rollout. So the model, the harness runs inside the sandbox. Whenever the harness needs LLM input, like reasoning and tool calls, it calls the inference servers that we host. So remember, we have to take some of our GPU nodes to host the model to be able to do this. And we repeat this thing, this calling and executing until the task is solved, or until at least the agent thinks the task is solved. Oftentimes the agent does not know whether the task is solved, but it has to understand and learn when to stop by itself. So for example, for SWE, for software engineering, the agent does not have access to the unit tests that need to be green for the verification to say that this is correct, but rather you upload them afterwards, also because otherwise the agent could just hack the rewards and just make the tests run green. Right, and so again, like we upload the tests or do whatever else kind of scoring you need to do. And then from the scoring, you have a bunch of metrics like, okay, the tests passed, some tests didn't, and then you can like derive a reward from this. So now you have a rollout and a reward essentially attached to that rollout. And then finally, as soon as you have a batch of these rollouts, you can send them to your trainer nodes. And these trainer nodes that you can see here, basically, they receive a batch, and then they do a training step, so the GPUs run this algorithm that I talked about, where they take a rollout and the reward, and then can get you the loss. And this loss can then, of course, be used to get to change the weights of the model as to increase the probability of higher reward in the long run. And finally, after the trainer is done, it has, of course, to update the model that is running on the inference nodes, because otherwise the inference nodes are, of course, doing rollouts with an old model version and not with the newest one. So it may basically, for example, if suppose at some step the model now is good enough to solve a certain task, of course, we want to now sample this task so we don't overtrain on things that are now easy and not train on things that are now not hard enough anymore, or like easy enough to solve. Okay, and then one thing that we learned in this, and especially I, because before I joined, I did not understand the scale and the severity of inference. Inference is actually so much more complicated than training, in my opinion, oftentimes at least, because inference can become quite the bottleneck. As you saw in the last slide, you have training nodes and inference nodes, and of course the trainer is waiting for inference to give it batches. And if the inference does not produce batches fast enough, then the trainer nodes are just waiting for work and are just idling, and you never want to have idling nodes, ideally. So the reason that inference is so problematic is that, of course, the rollouts have to be quite fresh. So you can't just generate them in advance and then just send them to the training nodes. You have to kind of get them whenever the new model updates. You have to not be too far, like the inference, the rollouts may not be too old compared to where the training nodes are currently with the model. And if inference lags behind, of course, training is going to stall. And then two techniques that we found that help quite a bit are, on the one hand, wide expert parallelism, and another is prefill decode disaggregation. Wide expert parallelism just means that instead of hosting the model, even if it would fit on one GPU, you just distribute the experts. These are like small parts of the model, essentially, in modern models, and you distribute them across a lot of GPUs, and that gives you more memory for KV cache, which KV cache is, for these long rollouts, something that becomes the bottleneck quite quickly. And then prefill decode disaggregation especially helps with these agentic workloads, because usually you have, when you think about a model, it just auto-regressively generates new tokens at a time. This is what we call a decode. So it only has to do the prefill, where it takes all of the user tokens at once at the start. And so normally, or like in previous times when we were doing reinforcement learning with reasoning models, which are single-turn, this was not really a concern. But now that we have a lot of prefill and decode, because each tool call essentially is just, again, a long string of text, like it could be the outputs of a file or the grabbing of a document, depending on some keyword, and this actually is oftentimes much more of a bottleneck than the decode. And so we disaggregated, so we have some nodes that do just prefill and some nodes that do just decode, and this is like a more advanced optimization that helped quite a bit. Then, as I said, we don't want to have nodes idling, so I want to really get across that reinforcement learning with LLMs is inherently asynchronous. That means that while the trainer is working, and calculating the loss, the inference nodes are also working already on the rollouts for the next batch, for the next training step. And sometimes it can be even asynchronous up to like a few steps. And so essentially, this means that we train on stale rollouts, right? At least one step stale, except for the first step, right? Because the first step is just inference. There's nothing to train yet. But then as soon as the inference is done, you send it over to the trainer computes the loss. And while the trainer computes the loss, you take your, you do more inference. And so we're always asynchronous, as you can see at the bottom there. This is kind of like something from our Intellect 3 paper, a very nice way to visualize this, where the bottom is basically the inference weights and the trainer is at the top. And then you can see that whenever we send rollouts and send weight updates back, it's always like a bit like asynchronous. And this is one source where the rollouts that we train on are older than, or like different from the model that generated them. But this can be even further, this can be made even worse if you consider that you have two different implementations of the model in code. One of them is in the trainer, and one of them is in inference. So the trainer is often in Megatron or FSDP or Torch Titan or whatever. And the implementation of it is just slightly different sometimes. Sometimes you have different kernels. Sometimes it's just because of the way that you get the batches, and it's just the reduction is different. You have a floating point non-associativity, of course. So these things all play a role in creating even a mismatch when you would think that actually the model weights and the model weights at the trainer and the model weights at the inference are the same. And this has been quite a big challenge. I would say this is one of the biggest problems that we faced when dealing with stability, because like these small mismatches, they accumulate over time, and your reward may go up, and you don't really realize it, that you're corrupting something inherently in the model, and at some point, after 1,000 steps or so, it just crashes completely. And this is one of the scariest things that you can see after running this training for more than a week across many restarts, and it's quite frustrating. So these are the two libraries that I'm most involved with and that we as Prime Intellect have made open source. They are, on the one hand, Prime-RL, which is our training framework, which is essentially this inference and training code that makes sure that you can get very good performance on many different models. We have custom implementations of many of the big models. We've been able to train 1 trillion parameter models quite efficiently. We have essentially we have something like bring your own loss function where you can just wrap in your own loss, so you don't have to use the one that we found to be best if you want to experiment. On the other hand, we have verifiers, which is our environments framework. And now I didn't really say what is an environment really, but I think for LLMs it makes sense, at least that's how we think of it, is just for it to be a task set and a harness. So you can just create your task set, you can create your harness, or you can use Claude Code or Codex or any harness that you want. And you can just train models with this stack, essentially. And yeah, so this is where we are. I talked about where we came from. I talked about where we are. Let's talk about some open problems and things that might be quite exciting. So the first one is long horizon tasks. Now, all of these tasks, so we started with math, which is not that long horizon. We went to something like software engineering, where we're now quite confident that we cracked the recipe. But these tasks are not as long horizon as, say, a whole game of Pokemon, right? So if you want the model to be able to solve tasks that are 30 hours, maybe even 50 hours, maybe even weeks or months on end, we don't really have the capability yet as a community to really do that. At least there's no proven recipe so far. One of the key problems is that, of course, we have one reward for the entire rollout, but if the entire rollout takes many months, it's very unlikely that the model will actually get to the correct reward because, well, there's just so much that can go wrong. So this sparsity actually becomes quite a problem. Something that may help that I think might be quite interesting is something like a replay buffer, where instead of always starting from the beginning of a task, you sample the model, and then you see the places where the model often, yes, performs quite well already, and then the pivotal moments where the model actually starts to completely deviate off the golden path. And then you just sample more there, and maybe you even do some reward shaping where you start from there and you guide it with reward for intermediate steps towards that golden path. But another thing, of course, on the infrastructure side, so this was just algorithms, on the infrastructure side, actually, we must be way more robust, because a sandbox having to stay up for 10 hours is one thing. A sandbox having to stay up for 2 weeks is quite a different challenge. It's more costly, so we need better infrastructure to make it not prohibitively expensive. But also, just infrastructure is going to be infrastructure, so you will have to find new ways of making sure that you can recover from maybe a corruption. Maybe you will have something like sandbox snapshotting, for example. This is one thing. Then non-linear rollouts are something that I'm quite fascinated by, which is basically like Cloud Code already kind of does it, or Codex as well, where they can call sub-agents, especially if you prompt them to, which then decompose the task into smaller subtasks, and each agent just gets all the information it needs and can work in parallel to solve this task. Kimi, for example, like the Kimi model series, experimented with something called agent swarms, I believe is the proper name, where instead of decomposing the big problem into smaller models, what you do instead is you just sample the same problem, but just with a swarm of agents, and then you just do something like majority voting to see what most agents think is the correct answer, and then you choose that, for example. But this opens up a whole nother can of worms. Now you have to worry, okay, what algorithm do I use? Can I just reuse the classical algorithms that were made and only where it was only envisioned for the rollouts to be linear? It's quite an open problem. Further, you have credit assignment, which is a very big topic where a lot of people have not really gotten into yet, in my opinion, but I think it's going to be quite big. Because, of course, one of the key things is that we have only rewards at the outcome, only when the model is done. We don't really have intermediate rewards, and we don't really have a way of saying, okay, this part of the rollout was good, so let's reinforce that, but not reinforce another part, and maybe even de-enforce that part. There's a lot of research going on there, but there's nothing been yet where I would say that we've cracked the code. Because also, like this saying, okay, these intermediate parts are good, these intermediate parts are bad, this is a value model, essentially, and value models are very hard, especially with LLMs. And then finally, of course, tasks at some point can also become a bottleneck. The nice thing about tasks is that once you have them, you can essentially reuse them a lot, because the model can just keep learning and generating its own training data, in a sense, by just running the rollout and so on, and we are reinforcing the reasoning and calling the tools. So we don't have to have the static data set, but as the models get better, the tasks that will be eligible for models to learn from will also grow slimmer and slimmer, and we will have to find very complicated ways actually to do that, to create tasks where they actually are the appropriate amount of difficulty. And I think my colleague Florian will also talk about evals suffering from a very similar problem, where a lot of evals cannot even tell apart whether one model is better or worse than the other, because models have gotten quite good. Okay, so what you should definitely take away from this talk are basically these three things. On the one hand, agents are real. So it's not just hype, it actually works. People use them in production, and you may not like it, it may not be to your taste, but and you may like coding by hand, and you can still do that sometimes, but I think you will stunt yourself quite a bit if you don't at least give the agents a try, especially nowadays. Then further, that scaling reinforcement learning in particular is quite hard, especially because of all the infra that is involved with hosting the model and sandboxes and everything that you don't really have to worry about when doing pre-training. And finally, that even though scaling is probably necessary for AGI, that is that the models that we currently have are probably not enough and would probably get us quite closer to a general intelligence through scale, it is probably not sufficient for something, for the reasons that I mentioned before, right? So you have too few tasks, maybe, as the models get better. Long horizon tasks are still very unsolved. And so it's necessary, but not sufficient. Yes, thank you for listening.
Yeah, thank you for the great talk, and I'm sure there will be questions for you. And we already have the first here.
Thanks. Many thanks for the talk, amazing talk. One question only. You mentioned you use for the task Docker images, and how do you orchestrate all these Docker images, especially what you mentioned before, with memory, CPU or GPU, and also how do you build these Docker images and push them? Do you have some automation in place, and does this change? How do you monitor it, and what is the challenge there?
Yeah, that's a great question. I think I don't have to repeat it, right? Because it was
exactly.
perfect, exactly. Okay, right. So so we have our own sandbox service basically. So we built up from scratch something that can spawn sandboxes, host images, and so on. This is not really the area that I've been most familiar with, so I can't really give you a satisfying answer probably. But just to say a bit about it, so we have our own service where you have an API that can create a sandbox, and the sandbox then can take parameters like how many cores and how much memory do you want. And then, yeah, I mean, as soon as you have this API, you just, in our code, whenever we have this environment, this orchestrator basically that holds all of the environments simultaneously, we just spawn for each task one sandbox and then install the harness inside there. Does that answer your question?
And if it's dying, the Docker image is dying, or
yeah, let me repeat it. So the question is, if the Docker image is dying. So do you mean that the sandbox is dying, or the Docker image itself that is on the hub?
Yeah, that is on the hub.
Yeah. So we have our own. So it's whether what we do when the Docker image dies on the hub. So we just host it ourselves. Yeah.
Wanted to go a bit in the background because
Thanks for the amazing talk. You mentioned that tasks are basically the bottleneck for RL, right? And also RL is very expensive. So for a new class of problems that one wants to solve, performing RL may not be, maybe just too expensive. So I'm wondering, like, is it when new tools become available, but the task remains the same, does one need to retrain the whole agentic pipeline, or is an RL model that generally has the understanding that tools can be used, can they generalize on newer set of tools?
Yeah, great question. Yes, it can generalize quite well. So the thing is that we build our abstractions in a way that we don't really have to tie the tools to the task. We can tie them both to the harness and the task. But if you train a big enough model, what we found is that even if you change the setup of the harness, that is, you change the way that it interacts even with the environment, so maybe it's a persistent REPL, or whether it's just bash or whatever, it just generalizes quite well, and especially if you have many diverse tasks.
Yeah, thanks for the talk. I'm a big fan of Prime Intellect. Follow you guys on X. I'm wondering, like, what happened? So you said that the agentic RL pipelines, they're training for tasks that are verifiable, so you have to give a reward. After you do that, what happens to the model's performance on tasks that are not verifiable, that require more creative type of thinking?
That's a good question. To be honest, we have not really done a lot with these more creative tasks, like creative writing or poetry or whatever. I think there's also a lot of tasks that are tied to capabilities that are also not verifiable like code, where you can just run tests. And so I think for writing and creative stuff, I wouldn't even know how to judge it. I mean, there's probably very smart methods. But for these other non-verifiable tasks that you can do something like scaling up the compute of the LLM judge and just letting it have more access to the underlying like code base and so on, and then it will often also be able to say, okay, the unit tests pass, but also the code style is conforming to what it is supposed to conform to, and so on. So I'm sorry, I can't really give you a satisfying answer probably for these creative tasks, but we'll work on it eventually.
All right. Very nice talk. You mentioned for like coding and longer horizon tasks, the like outcome only rewards being a problem. Also, often, of course, like for SWE bench. Closer? Okay. For SWE bench similar tasks, you have 0 or 1, I don't know, tasks passed in the end.
Yeah.
Do people actually train with those tasks directly already? So
You
then
mean
curriculum learning stuff, or do they modify those environments somehow to get like a more smooth reward or something?
Do you mean whether they train on the eval on SWE bench?
No, not
Okay.
on the exact evals, of
Yeah,
course,
yeah.
but on
this sort of tasks.
Yeah,
Yes.
I mean SWE Smith or something like
Yeah.
that.
Yes, exactly, on these
automatically
tasks.
generated. Yeah, okay, and
Yeah.
they
So
it
they are-
works even with the 0-1.
Yes,
rewards.
it works surprisingly well. The key is that before you start the training, you probably do a pass with a smaller-ish model
have a
that is already
curriculum.
quite good, and then you can tell which tasks to, for example, not sample at the beginning.
Yeah, okay.
Yeah.
Yeah, of course. Yeah, thank you.
Thanks for the amazing talk. You made it quite clear that it's important to have the right level of difficulty for the tasks. Do you have a way to judge if it will be a good level of difficulty before you start training, or maybe even if you start training and realize it's too easy or too hard to adapt the difficulty?
Yes, let me answer the second question first. We have something that we call difficulty buffers. And so, for example, what happens is that if we see, so the way that we train is we use something similar to GRPO, which is that you sample multiple rollouts on the same problem, from the same problem, and then you do a comparison between these rollouts and see, okay, which were good, which were bad, and so on. And you derive the advantage, that is the reward, but for training, from this. And if we see that, for example, with group size 16, that a task was not solved by any model, by any of these rollouts, or it was solved by all, we put these into specific pools that makes it either completely impossible for them to be sampled again during the training, or just less likely. And then we reintroduce, for example, the difficulty, like the ones that were too difficult at the start, we introduce them gradually back into the entire pool. So this is a very naive way of doing it, and it works surprisingly well. And the first question is, before training, it's quite hard, because usually the models that we train are base models, and so you can probably, so what I would imagine would work quite well is that you just take the model that you are about to train and just do inference 8 times, for example, for every single task, if you can afford that, or just if all tasks have roughly the same difficulty, you can just do it spottily, like just do some. Or again, you can just use a smaller model, as I mentioned earlier, and then you can quite quickly see, okay, if a small model that is already post-trained quite a lot on software engineering, and it can't solve these tasks at all, then the base model that we're just training, even if it's bigger and supposedly is going to be better at the end, might not work right now. So we basically also do some filtering at the beginning.
Thanks for the great talk. I had a couple of questions. First one would be that, so how do you assign rewards, especially for non-verifiable tasks? So do you do that via human feedback? And if so, then how would you scale up RL if human judgment would be a bottleneck?
We don't do it with human feedback. We do it with LLMs as a judge. So you just have an LLM simulate a human, essentially. But we do it in a way where instead of training a reward model to do that, we have something called rubrics, where it's basically just categories of different things we care about, like say code style and maybe not adding too many comments to the code or whatever. And then the judge basically just can look at it and say, okay, the agent clearly solved the task, the unit tests pass, but the code style is terrible. He does not. It's not linted maybe, or it's he does not honor the contracts of, or like he does not mimic the style of the other files in the code base. And so then it can say for this rubric, I give a reward of 0 or I give a reward of 1, and then we can sum over this and just normalize between 0 and 1, and that can be the final reward, basically, if that makes sense.
One other question would be that, let's say you have a bunch of tasks, right? Say a batch of tasks, and you get a checkpoint or a model in between, and you want to basically judge how good it is. That is, you want to assign a reward to it, and it performs differently on different tasks. So for some tasks, it's very good, but on some tasks, it's very bad. So how do you reconcile these differences in rewards?
So I think the way that we would go about it right now, so if you've done your difficulty filtering at the start in a proper way, then okay, so some environments will inherently have a faster learning curve than others, right? And like you can't really, even if you do the difficulty filtering perfectly, and they all start with, let's say, 20% solve rate, some will get quite quickly like saturated, and others will take much longer. So I think this is kind of what you're hinting at, and it's the way to go about it right now is that we just manually like change the distribution of tasks that the model sees. So we upsample or downsample. But of course, I imagine, and I'm pretty sure, and we're already working on this, that longer term, actually, we will have a more automated way of defining and deciding which task to sample right now, essentially. But it's still very naive and handpicked. We just restart the training from this checkpoint with a different, like, upsampled or downsampled task distribution.
Thank you, and I think with that we are at the end of this time slot, and yeah, I'm sure Konstantin will be around for further questions in the room or somewhere outside. Let's thank him again. Thank you for the great talk, and see you later.